Okay, so the first thing is I don't have your binders. I mean, I have them. I just don't have them graded. Sorry. So I know what I need to fix. Next time I'll go better. But I won't give you any homework to do over break. And I will definitely have them back for you when break is over. So you'll get them back on the Tuesday after spring break. If anybody, like I said, if anyone particularly wants it, you know, you're planning to do a lot of work over break or something and you want your own notes, just come with me back to my office after class and I can give it to you and then I'll grade it when we get back, you know. But you might just be fine with the notes that are posted online too. So just think about that. All right, and then today I want to do one more example problem, and then I want to spend the rest of the time just giving you problems to work on together, and then I'll go through them. I don't think there's any reason to go into new material, you know, before a week-long break. So, okay. Anybody have any homework questions or anything before I start with that? All right. So we're going to keep doing distributed loads, and the only way we can work with distributed loads is if we have a horizontal beam. There are ways to deal with it if they're at angles, but we're not going to go into that. And so let's say we have a pin joint at the right, a roller at the midpoint, and then a distributed load with a triangular shape, maximum 5,000 newtons per meter. Let's say that this is 1 meter, this is 1 meter. And let's say that the mass of the beam is 50 kilograms. And we want to calculate the reactions at those two joints. So this is the first example I've done where you have a distributed load that doesn't act over the whole shape. So let's draw a free body diagram. There's a weight force, and that acts at the middle. I'll just put it here because it'll keep the picture from getting too jumbled. So 50 times 9.81 is 490.5. And then we have the distributed load. (5,000 newtons per meter). And then we have to think about the joints. Let's do one more thing, actually. Let me put a force this way of 4,000 newtons. Okay, so at the pin joint, what kind of loads are applied? Yep, two components of an unknown force, so I'll call that R. And then at the roller, what kind of load is applied? That's right, it's just this way. That's perpendicular to the surface it's rolling on, so perpendicular to the ground and toward the chosen body. And I guess let's call this one RA, the one from the roller, and then this one RB. And the next thing we have to do is represent that distributed load as a point force. There's the triangular shape. The base has a length of 1. The height is 5,000. And so the area is 5,000 times 1 over 2. So 2,500 newtons. And then the location of that point force is at the centroid. And so what's this distance? Well, so let's think about it this way. Coming from one direction, the distance is 2/3 of the base. Coming from the other direction, the distance is 1/3 of the base. Is this 1/3 of the way or 2/3 of the way from this side? 1/3. So, and the base is 1, so this is just 1/3. So now I'll redraw this free body diagram. We have the force vector RB. We have the upward force RA. The downward force 490.5. The horizontal force of 4,000. And then over here we have the downward force of 2,500, where this distance is 0.3 repeating. Now Newton's second law. We have the 4,000 Newton force in the negative x direction. We have the downward force of 2,500, so that's 0, negative 2,500. We have the downward force of 490.5. And we have that unknown force vector RBX, RBY. And I missed the RA. We also have 0, positive RA. And then the moment equation. We have to choose our about point. I think this is probably the easiest one. So first, for that force RB, when you're dealing with a horizontal beam like this, you're only worried about the vertical components producing moments, because the horizontal loads always have a line of action straight through whatever your about point is. So what's the moment arm for this point, for that force RB? 0, that's our about point. Then what's the moment arm for the 490.5 force? 1. The force is 490.5. And would that make it rotate clockwise or counterclockwise? That would make it rotate counterclockwise, because remember, you're imagining it's rotating around that out point. So counterclockwise means positive. And then the force RA is at the same point, so it has the same moment arm. So that's 1 RA. And would that force make it rotate clockwise or counterclockwise? That's clockwise, so minus. And then the 2,500 Newton force. What's the moment arm for that one? Yeah, that's right. So from here, it's 1 meter to get here. And then this whole thing is 1 meter. So 1 plus another 1 minus a third. You know, you can think of it that way. So 1.6 repeating. Times 2,500. And is that clockwise or counterclockwise? That's counter, so positive. And the only force we have left is the 4,000. 1, 2, 3, 4. Yeah. And that's horizontal, so that doesn't produce a moment. So all this adds up to 0. And so now we have our system of equations. So first, RA is equal to 490.5 plus, I think that's 3,333, right? And so RA then is equal to 733.83 repeating. Yep. Yeah, so first calculate just the absolute value, the distance, and then do the sign from which way that force would make it rotate. So no matter which way you're going, just call that a distance of 1, that's a distance of 1.6 repeating. Okay, yes, I figured that was likely. For this? Oh, I was way off. Okay, 40,000 what? Okay. And then Adam, what do you get there? 4, 6, 5, 7.5. Okay. And then plug that into the other two equations, and you get that RB is equal to positive 4,000. And then, boy, I cannot do that one, that's for sure. Okay. Okay, so think about the directions here, because this is sort of interesting. So we got positive for RA and then positive negative for RB. So this is saying that obviously this roller can only produce forces in one direction. It can't pull down. If you imagine this force being applied over here somewhere, that has to push up to keep it from swinging down. And then in the x direction, there's only one external horizontal force going that way, so this has to pull this way to keep it from accelerating. But the y component of this force is actually pulling down to keep this in equilibrium. And that's because this is trying to rotate the thing like this. And so to counteract that, if you think of this as sort of the force over here and the force here are fighting to rotate it around that point, sort of, then this is trying to rotate it counterclockwise. That means this has to try to rotate it clockwise. And so that force has to be down, even though, you know, that seems a little weird when you think about the fact that these are both trying to support a downward force. You'd think they both have to be up, but that kind of stuff happens. Any questions about that one? No, I just made that up, but I know there is a homework problem sort of like that. Okay, so now let's say that you have a beam, makes frictionless contact with a wall over here, and there's a pin at the other end. And let's say at the middle, there's a horizontal force of 1,000 newtons. Let's say that there's a downward force here of 5,000 newtons. And then on the second half, let's say there's a distributed load of 2,000 newtons per meter. Let's say this distance is 0.25 meters, and this distance is 0.25 meters. Mm-hmm. So I just moved it up here so it made the picture look cleaner, but that's a force going horizontal that's applied here. You could think of that as this part of the beam is attached to some machine or something that's pulling this way. Or, you know, a lot of times the way this would come up is you do a free body diagram of a second thing that's connected, calculate that for it to be in equilibrium, you needed this to be applying a force to it that way, and then Newton's third law says that being, you know. But think of that as just something attached to it, applying that force. Okay, so we want to calculate, and let's give it a mass also. Let's say the mass is 20 kilograms. What are the reactions? So what we're really trying to do is calculate, we want to get to the point where we know all the external loads acting on this body. Right now we know all the external loads except the force here and the force here. And we want to get those because later when we go into calculating the internal loads in the beam, we're going to need to know those, and this will be like a starting point. Okay, so see if you can work through this. Talk to the people next to you. Move around the room. Make noise, like grunting noises and stuff, because it's hard work. And all right, yeah, let me know if you have questions, and then I'll go through it after you have some time. Okay, so free body diagram. There's a weight force that acts right at the middle. That's 20 times 9.81, so 196.2. There's an unknown force vector at the pin. Call that RA. There's a horizontal force at the middle of 1,000. There's a downward force of 5,000 halfway between the middle and the right end, and there's, at that same location, there's the force applied by that distributed load. And that distributed load has a base of 0.25 and a height of 2,000. So the area is 0.25 times 2,000, so 500. So in that same place that there's the downward force of 5,000, there's also a downward force of 500. And then at the frictionless contact, there's a force that's perpendicular to the surface toward the chosen body. So this way, and I'll call that force RB. And for that force RB, let's think about the direction of that force. So the way I like to do that is, we know that it's 30, so here's our positive x-axis. We know that it's 30 degrees from the positive x-axis to the incline. That's the angle that's actually drawn. So I'm going to draw a vector like this that's parallel to the incline. Okay, we know that that's 30 degrees. And our contact force is perpendicular to that. So now we have another force like that, and those are in a right angle to each other. So to come up with the angle for this force, you just go plus 30 plus another 90, so theta is 120. Any questions about that angle? All right, so now we can go through the calculations. Newton's second law says RAX, RAY plus negative 1,000, negative 196.2 plus 0, negative 5,500. Anything, any forces acting at the same point, you can just add them up. And then this force is RB times cosine and sine of 120. So that is negative 0.5 RB, positive 0.866 RB. Is equal to zeros. Let's see, so we got force 1, 2, 3, 4, that's it. And then the moment equation, we have to choose an about point. I'll choose it over here. So there's no moment produced by RA. Do either of these two components, the 1,000 or the 196.2, produce a moment? Which one? The 196 does, the 1,000 doesn't. The moment arm there is 0.25. So 0.25 times 196.2. And then clockwise or counterclockwise? Yep, that's clockwise, so that's negative. And then the force of 5,500, what's the moment arm for that? Yeah, that's halfway between 0.5 and 1. So that's 0.375 times 5,500. And is that clockwise or counterclockwise? That is, yes, that's also clockwise, so negative. And then you can think of that RB as, we've already broken it up into a horizontal and a vertical component. So you can do the same thing just with the vertical component of that RB. We have a force of 0.866 RB, a moment arm of 0.5, And so we have 0.5 times 0.866 RB. And then is that positive or negative? That force would make it rotate counterclockwise, so that's positive. And those add up to 0. Solve that, and what do you get for RB? What was it? 4876.42. Okay, and then you can plug that in and solve for RA. And what do you get for RA? 1473.1 newtons. Any questions about that? Yeah. Okay, so these forces are acting exactly in between this and this. And so you can just average those 2 points. Here we had a moment arm of 0.25. Here we had a moment arm of 0.5. This is right in the midpoint, so the average is, the average of 0.25 and 0.5 is 0.375. You can do it that way. Or you can just think, this length is 0.25, and so you're going to start at 0.25 and go half of 0.25 to get here. Either one of those ideas works. But I really like that midpoint thing. It works with vectors too. It works with coordinates of points. If you know the coordinate of one point, 400, 743, and then you know the coordinates of the other point, -50, -864, and you want the midpoint between those points, just take the average of each of those two coordinates and it gives you the coordinates of the point. Good trick. Any other questions? Okay, so the next one. We have a pin joint over here. And this beam is horizontal for 1 meter. And then bends down like that. And at this end, there's a pin and slot joint. I'm going to need to change something here, but this angle is 20 degrees between the slot and the vertical. This is 1 meter. This is 1 meter. This is 1 meter. And then at the midpoint of the diagonal part, we have 2 little extensions. So each of those extensions, it looks a little asymmetric, but each of those extensions is 1/2 meter. You see what I'm getting at there? Okay, and now the external loads, we have a distributed load like this. That's 1,000 newtons per meter at its maximum. And then on the ends of these two extensions, we have a 200 Newton force there and a 200 Newton force there. And we want to calculate the reactions. Ignore the weight on this one. Okay, anyone have any questions before you start? All right, yeah, let me know if anything comes up. So first, free body diagram. There's no weight in this. There's a 200 Newton force this way, 200 this way. There's a force from that triangular distributed load. And that triangle has a base of 1 and a height of 1,000. So the total force is 1 times 1,000 over 2, 500 newtons. The centroid is here, where this distance is 1/3 of the base. So this distance is 0.3 repeating. And so that distributed load applies a force of 500 newtons there. And then all we have left are the force from the slot and the force from the pin. At the pin, we have an unknown force vector. I'll call that RB vector. And then the slot is like that, and the force is perpendicular to that line. So the force vector is this, where that's a 90-degree angle. The way I drew it, it looks like it's straight along the line of that beam, but it's not. And I'll call that RA. And there's a couple of things we have to figure out. Well, I guess really the main thing is we need to figure out what the angle is of this vector. The easy way to think about it, if it occurs to you, or I should say maybe not the easy way, but the fast way, is to think if that slot was perpendicular, a vector that's perpendicular to the slot would be exactly horizontal. Well, we're tipping the slot 20 degrees that way, so that would tip this perpendicular up 20 degrees. And so the angle of that force vector is 20 degrees counterclockwise from the x-axis. But if that doesn't occur to you, the sort of thorough way to do it is draw the coordinate system. And now we know that this slot makes a 20-degree the downward vertical vector. So I'm going to draw a vector parallel to the slot like this. So this angle's 20 degrees. And then the vector we want is perpendicular to that. So those two are at a right angle. And now just add up the angles. From the positive x-axis to get to the downward vertical, it's minus 90. Minus 90 plus 20 gets you here, so we're at minus 70 here. And now add another 90 in here, plus 20. And then that's probably where you go like, oh yeah, that other is obviously 20. I should have thought of that first. But don't beat yourself up about it.
How do you do that?
Yeah, so if you go counterclockwise, it's positive, and clockwise, it's negative. So I went minus 90, minus 70, minus 70 plus 90 is plus 20. So it's negative whenever you're going clockwise, positive whenever you're going counterclockwise.
So if I go, how did I manage something? Let's say, 92 minus.
You could go all the way like this and go 270 to here, plus another 20, 290. And then another 90, 290 plus 90 is 380, which is the same as plus 20. So if you want to just go counterclockwise, you can just go counterclockwise. Any other questions about that? Okay, so now I'm going to write out the table because this beam isn't horizontal. So rho, force, moment. And we have to decide what our about point is. I think I'll put it here. Okay, so what we're going to do now to calculate these row vectors is we're going to imagine that our origin is here and just calculate the coordinates of all these points. So first, the force RA, that's at the about point, so no row vector. RB, yes, thank you. The force vector is RB, X, and Y. And the moment is 0. The next one is this 500 Newton force. That's over, okay, so we know that it's 2/3 of the way from here to here, and this distance is 1. So that's just 2/3 of a meter from here to there. You have to go in the negative X direction. So that's negative 0.6 repeating 0. The force is 0, negative 500. And so the cross product is positive 3.3 repeating. What? Yes. 333.3 repeating. Okay, and then now we're to these two, those two forces that make up that couple. Okay, so how far do you have to, if this we're shooting at the origin, what are the coordinates at this point? It's negative 1.5, and then you haven't gone down at all, so the row vector is negative 1.50. The force vector is negative 200, 0. And so there's no moment from that one. Then what are the coordinates of that other 200 Newton force? Yeah, negative 1.5, negative 1. And that force is positive 200, 0. And so the cross product is positive 200. And then the last force is this force RA. So to get there, you go negative 2 and then negative 1. The force vector is cosine and sine of 20 degrees times RA. So that's 0.940 RA, 0.342 RA. And the cross product is, I can't do that one, negative 1.54 RA. And now, Newton's second law says RBX RBY plus 0, negative 500 plus negative 200, 0 plus positive 200, 0 plus 0.94 RA, 0.342 RA is equal to zeros. Okay, what do you guys get? 0.256. Okay. Positive?
Yeah.
And then the moment equation says 333.3 repeating plus 200 plus 0.256 RA is equal to 0. So what do you get for RA?
Negative 2083.
Negative 2084. Okay, so that's our RA. Does it make sense that, we said that the direction is this way. This is a pin and slot joint. Does it make sense that we got an answer that says it's actually the other way? A lot of times, with a lot of problems, that'll tell you something went wrong. But with a pin and slot joint, that can apply a force either of those two directions. So that's just saying the real force is 2084 pointing this way, the opposite direction. And then for RB, what do you get for those? Okay, and then get anything different than that? That's it. Any other questions about this problem? All right, have a good spring break. Okay, positive. Good.